Okay, now that we have discussed Hubble's law, the next question is, why is this value of h sub 0 so special? So every year there are astronomical conferences, and astronomers from all over the world gather together and they argue about how big or how small h sub 0 ought to be. So currently we think it should be 22, but there are some astronomers that say no, it should be larger than that number. There's others that say it should be smaller. So what difference would it make if h sub 0 was either larger or smaller than 22? So there's going to be 4 reasons which we're going to discuss right here. So the first one is that Hubble's constant is going to determine cosmic distances. And so we're going to be making use of this formula here, that r is equal to v divided by h sub 0. So we already did this one. So this was equation 20.3. And so we calculated the speed by knowing how much of a shift there was in the spectrum of like hydrogen. And then we calculated what the speed of recession of that galaxy would be. And then we divided it by 22. And then that told us how far away the galaxy was. Okay, so here's our working equation. So what difference would it make if h sub 0 was actually larger than 22? Okay, so if we put a larger value of h sub 0 into this equation, notice it's in the denominator of the formula. So the bigger you make the denominator, the smaller the r is going to get. So our measured distances of faraway galaxies would be smaller if we choose a larger value of h sub 0. All right, let's try another one here. So the second reason why h sub 0 isn't so important is because it determines the age of the universe. So now this one is pretty tricky, okay? First, we have to remember that speed is equal to distance divided by time. All right, so that means we could rearrange it and say that r is going to be equal to v times t. Okay, now the next thing that we're going to do is take this equation up here, solve it for the letter v, so that means v equals r times h, and then take that and we're going to put it here. So now we've got that r is going to be equal to r times h sub 0 times t. And then this r on this side cancels this r on that side, and then we could solve it for the letter t, and we get that the age of the universe is going to be equal to 1 divided by h sub 0. Okay, so that is, now this is not a actual equation, this is a proportion. So I really need to get rid of that equal sign and then put in a proportional thing. So it's approximate. All right, so what difference is that going to make? So here's a sample question that might be on the exam. If Hubble's constant is actually larger than what we think it is, how would this affect the age of the universe? All right, so we're going to put a larger value of h into this equation. The h is on the bottom, so that means that what comes out gets smaller. So therefore the age of the universe would be less. And so maybe instead of the age of the universe being between 12 and 14 billion years old, well then maybe the age of the universe is only 10 billion years old. So it makes a big difference as to what value of h sub 0 that you use. All right, let's now do another one here. So Hubble's constant is going to determine the expansion rate of the universe. So we think that the universe is expanding. Space and time are expanding. And part of that is because of the Big Bang. And then later, in another episode, we're going to talk about dark energy, which is causing the universe to expand. So the expansion rate, how fast is the universe expanding, is going to be related to Hubble's constant. So we can take this equation up here and rewrite it so it says V equals something. So velocity is going to be equal to h sub 0 times r. And this shows that the speeds of galaxies depend on the value of Hubble's constant. So if Hubble's constant gets bigger, then the speeds get bigger. If Hubble's constant gets smaller, the speeds get smaller. Okay? So the faster the faster the speeds, then that means the universe is expanding faster. So therefore, the expansion rate of the universe is going to be proportional to h sub 0. So what difference does that make? So if Hubble's constant is actually larger than what we think it is, how would this affect the expansion rate of the universe? So if we make h sub 0 greater, notice this time it's in the numerator, so that would mean that the expansion rate is going to get faster. A larger h means that the universe will be expanding faster. And then we have this one here. So Hubble's constant determines the amount of mass and energy density the universe would need in order to stop its expansion. Okay. So first of all, what do we mean by density? So density is given by the letter rho, as in row, row, row your boat. And it's equal to mass divided by volume. So that as you increase the mass and then you keep the volume constant, you increase the density. So that's the definition of what density is. However, according to Einstein, energy is equivalent to mass. So E equals mc squared. Okay, so that means that mass can be turned into energy and energy can be turned into mass. So this is the reason why we call it the energy, the mass energy density, because it's not just the mass that contributes to the density of the universe, it's also the energy of the universe contributes to the density of the universe. Okay, now what does mass do? Okay, mass causes gravity. So gravity is what's trying to pull the universe in. And then in our next lesson, we're going to be discussing about things that are causing the universe to expand outwards. Okay, so this formula here is, I'm going to give you this formula in a future lesson, but it says that the density of the universe is equal to 3 times Hubble's constant squared divided by 8 pi big G. Okay, now do you remember what big G was? So big G was the gravitational constant. So it's the thing that's trying to pull the universe in. On the other hand, Hubble's constant is related to the expansion rate of the universe, which is causing the universe to expand. Now, which one's winning? So is gravity winning and the universe collapsing? Or is h sub 0 winning and is the universe expanding? Well, it all depends on the mass density of the universe. So if the mass density of the universe is large, then it's going to cause a lot of gravity. And that will slow down the expansion of the universe and eventually might make the universe collapse. If there's not a whole lot of density to the universe, then the expansion is going to continue forever and ever. And so we'll talk about both possibilities in a future lesson. So don't worry about how this formula is derived, because it's derived by using general relativity. But I just want you to see that the critical density is going to be proportional to Hubble's constant squared. All right, and then if we wanted to, we could put in the 3 and the 8 pi thing in there. But what's really important is that it's proportional to h squared. So let's try a question here. If Hubble's constant is actually larger than what we think it is, how would this affect the amount of density needed to stop the expansion of the universe? So if h sub 0 gets bigger, then that means the critical density of the universe is going to get bigger. So that means it's going to take, the universe is going to need to have more mass and energy in order to stop the expansion of the universe. Okay, so h sub 0 is very, very important. So you can see all of the different concepts in astronomy that are related to h sub 0. All right, so we are going to take a quiz. So let's take a break, and when we come back, let's take a quiz over what you've learned today.